back, kids and coaches. This is Coach Colin. Today I'm going to teach you how to throw the most wicked curveball of all time. So first step up, we're going to throw it. Get a little gas to the bag, we're going to throw some heat. Get up there, get the ball as hard as you can. Guarantee you strike out every time. And never forget, kids, never bunk. The physics principle behind a curveball is the Magnus effect, which is the commonly observed effect in which a spinning ball curves away from its principal flight path.
Generally, the Magnus effect describes a law of physics that makes a curveball curve. A fastball travels through the air with backspin, which creates a high-pressure zone in the air ahead of and under the baseball. The baseball's raised seams augments the baseball's ability to develop a boundary layer and therefore a greater differential of pressure between the upper and lower zones. The effect of gravity is partially counteracted as the ball rides on and into increased pressure. Thus, the fastball falls less than a ball thrown with spin during the 60 feet 6 inches it travels to home plate. On the other hand, a curveball thrown with topspin creates a high-pressure zone on top of the ball, which deflects the balls downward in flight. Instead of counteracting gravity, the curveball adds additional downward force, thereby gives the ball an exaggerated drop in flight.
Now let's take a deeper look of the Magnus force. The picture that is showed right now represents the effects of the air on a ball traveling from left to right. This side is moving faster due to the combined effect of the direction of flight and rotation. The stream of air breaks away from the surface of the ball, leaving a turbulent space. The ball is rotating away from the direction of the flight, so the airspeed over the surface is lower. The stream of air tends to cling to the ball, and so it deflects the stream of air downwards. The force pushing the ball down results in an equal and opposite force pushing the ball up. This force perpendicular to the flight path and the axis of rotation is the Magnus force. There was once a debate on whether a curveball actually curves or is an optical illusion. In 1949, Ralph B. Lightfoot, an aeronautical engineer at Sikorsky Aircraft, used wind tunnels tests to prove that a curveball does in fact actually curve. On whether a curveball is caused by an illusion, Baseball Hall of Fame pitcher Dizzy Dean has been quoted in a number of variations on the basic premise: stand behind a tree 60 feet away and I'll whomp you with an optical illusion. However, optical illusion caused by the ball spinning may play an important part in what makes curveballs difficult to hit. The curveball's trajectory is smooth. However, the batter perceives a sudden, dramatic change in the ball's direction. When an object that is spinning and moving through space is viewed directly, the overall motion is interpreted correctly by the brain. However, as it enters the peripheral vision, the internal spinning motion distorts how the overall motion is perceived. A curveball's trajectory begins in the center of the batter's vision, but overlaps with peripheral vision as it approaches the plate, which may explain the suddenness of the break perceived by the batter.